All right, so we will finish a section 1.8 on operations on function with one more operation, very important operation called composite functions. Well, so oftentimes we need to rely on one value to get another value. That doesn't necessarily mean the relationship between the dependent variable to the independent variable. Sometimes that independent variable depends on another independent variable, so it ends up being a dependent one in a way. For instance, when buying life insurance, the amount depends on age. But wait, age also depends on a third party variable, on another variable, which is what year you were born. So this will represent a composition of function. It can be written as a premium of age of year. So a composite function is defined similarly, and it's read as f of x, f of g of x, right? So it's this composition here, f of g of x, which is this function. And well, to identify a composite function, you would see this circle right here. No, it's not a multiplication symbol. The multiplication symbol would be f times g. This is not equal to f bubble g. When you see this bubble right here, that bubble means composite, all right? That means composition. And well, that is the function gets evaluated not at a value, but in this case at another function. For instance, let's have a look at one example and describe how we do these compositions. Well, so number one, let f of x equals, let me highlight the functions with different colors. So let f be 4x plus 3 and g be 2x squared minus 5. So they're asking us to find the compositions f circle g, that is f composite with g and g composite with f. All right, how do we do about it? Well, how do we go about it? Well, number one, let's use this notation. So every time you have the circle notation, it would be better to change it to the second notation because it's more descriptive, it's easier to understand. So that means the second function we write in this case, which is g, that's the inner function. So right? Well, so what are we going to do here? So think of the function f evaluated at g. So that means the function f, which is 4x plus 3, but instead of x, we're going to write the function g of x. All right, because we're evaluating a function at another function, not at one value. The evaluation at one value will come later, right? So let me highlight with the corresponding color so you can see what we're doing. So here we're evaluating at g of x, the function highlighted with green, and all we do here is simply substitute 4 times the quantity in green plus 3, where the quantity in green is what? 2x squared minus 5. So we just replaced with the actual function. All we do is distribute the 4, that is 8x squared minus 4 times 5, which is 20, plus 3. All right, and well, if there's any like terms to combine, all we do is combine the like terms. In this case, negative 20 plus 3 equals to negative 17. So we just created a new function by composing two functions. No, in this case, we didn't add functions, we didn't subtract functions, we didn't multiply functions, which this symbol again could be deceiving, could look like a multiplication, but no, it's not a multiplication, it's composition. And we didn't do division. Again, we did a composition of functions, which is a function evaluated at another function. All right, well, so let's have a look at letter B. For letter B, we're going to evaluate g at f of x. Again, the function we write inside of the big parentheses is the second function we read from left to right in our composition notation. Well, but again, we're going to evaluate this at f, Well, f, again, remember how we highlighted with yellow, so we can relate it to what we're substituting. All right, let me do equal the function g, and be careful here, function g, which is 2 times x squared minus 5 to quantity squared minus 5, and the quantity squared in this case, for now, let's call it f of x. All right, let me highlight it so you can see where it's coming from and how to relate it. Well, let's substitute 2 times the function f, quantity squared, minus 5, that is 4x plus 3. Okay, well, so that equals, well, over here, 2 times 4x squared plus 3, well, squared, 4x, no, not 4x squared, 4x plus 3, quantity squared, it's the same as saying 4x plus 3 times itself, and simply FOIL this. All right, so foiling this, that should give us, save the 2 for the end. Don't forget this, is what's it called, this negative 5. Be careful with this negative 5. So that is 4 times 4x times itself, that's 16x squared, plus 4x times 3, that is 12x, plus another 12x plus 9. And don't forget to subtract the 5. Keep carrying it. All right, this will result into, okay, combined like terms, that is 2 times 16 plus, 16x squared plus 12x, oh wait, combined like terms, 12x plus 12x, that's 24x, and plus 9, and then subtract 5 from there. This will be, okay, we can distribute the 2, that'll be 32x squared plus 24 times 2, which is 48x, 2 times 9, which is 18, minus 5, and well, 18 minus 5, is that equal to 13? All right, that equals then 32x squared plus 48x plus 13. As we can see right here, these two results, they're different, which is actually the general case. Something to notice here, that the order of the composition matters, and that's something we want to highlight here. The order matters when we work with the composition of functions. There's only one case in which the order of the composition won't matter and will give you exactly the same result, but that's something that is going to be left for pre-calculus, not for this course. All right, so let's use one of the results from part A or B to evaluate f composite g at 3. Well, so they're asking us to evaluate f composite g, that is, okay, let's highlight it. That means it refers to this function right here, to 8x squared minus 17, evaluated at negative 17. All right, so that'll be equal to 8 times 3, which is the value we evaluated at, squared minus 17. That equals 3 squared, which is 9. 8 times 9 minus 17. 8 times 9 equals to 72 minus 17, which equals to 55. All right, so in this case, they're not asking us to evaluate the other composition around, just this composition. All right, okay, so let's move on to another example. All right, so example number 10, let f of x equals to 1 over x squared and g of x equals to square root of x plus 2. Find f evaluated at g. This time, notice they didn't give us the circle notation, the f bubble g. But most importantly, guys, well, in some cases, they're going to ask us to find the domain. Why in this case? Because, hey, look at these two functions, guys. So these two functions have restrictions. So in the previous example, and let me go back real quick, what did we have? Polynomial whose domain is all real numbers, and then another polynomial whose domain is also all real numbers. So if we composite a polynomial with another polynomial, what did we get? Compare the two results. Aren't they both polynomials? And what's the domain of a polynomial? Well, it's all real numbers, and it's also because the the domain of both functions that made up the or that composed the function didn't have any restrictions. All right, so f of g of x. So number one, um, let's evaluate. Let's highlight first. I'm gonna highlight g with green. Hold on, that's not green, that's blue. So that's green. And let's highlight. Do I need to do the other one? I don't think we need. Anyway, all right. So number one. So f evaluated at g of x. That'll be equal to f, which is 1 over x squared. That is some quantity squared. All right. So let's see about this. So this will be. Let's put g of x for now. All right. So let's put g of x, okay, and this will be 1 over the function g, which by the way should be highlighted with green. Let me do that with green, okay, and that is the square root of x plus 2 quantity squared. And well, again, careful, the square cancels the radical. All right, square cancels the radical. So number one, that'll be equal to 1 over x plus 2. All right, so that'll be our composition of functions f evaluated at g. But be careful here because we have a little problem here when it comes to the domain. Number one, if we look at the new function right here, 1 over x squared plus 2, the domain of this new function that I'm actually following with the cursor here, has only one restricted value. That is, it won't be defined for x equals to -2. All right. So, well, that would be the domain on real numbers except x equals to -2. However, this function has more restrictions based on what? Number one, based on the restriction for this function right here. Again, for the radical function x plus 2 cannot be greater, or it's greater than or equal to 2. X is greater than or equal to -2. All right. So in this case, that means on the one hand, so we need to find the intersection between x cannot be -2 and this other set. Let's draw both sets. So number one, so I'm going to put this -2 over here as an open circle and represent that domain. All right, and then I'm going to represent as a full circle here, or as a bracket as we have done it in lecture, in class. Either way, it doesn't matter. So that's -2 and 2. So we are going to, okay, let me highlight with blue over here so you can see the colors, the good colors overlapping. So I'm going to highlight everywhere except where the hole at -2 is. That is all this. And for the radical function, I'm going to highlight with red everywhere to the right of -2 is supposed to be a negative, not positive. So this is -2 to the right because of this inequality here. All right. So I would need to look at the overlap of these two sets. So these two sets would overlap. Let me do another set right here. So this would be -2, and this would be this blue. Is that the blue? No, that's the other one. So yes, this is the one. And I'm just going to highlight where the two overlap, where the two where the two colors blend into a shade of purple here. And let's describe the domain. So the domain in interval notation, so domain, again, the overlaps of the two sets, this would be between -2 and infinity. All right, between -2 and infinity. All right, So let's move on to the next example. All right, so to move on to the next example, evaluate, or rather to part B of the same example, actually, it's to use this composition to evaluate this at -2. Actually, hold on, they're asking us to, what's it called, to evaluate the composition the other way around, not f of g, but g of f. All right, well, so there's a couple of ways we can do this. Number one, we can come up with what's it called, with the value of f to f of -2 and then substitute it into g, or come up with the actual composition. This time I'm just gonna do, I'm gonna work it inside out. I'm gonna find f of -2 on the side. Let me use a different color for that. That'll be f at -2, and that equals the function f, which is this function right here. All right, and that equals 1 over -2 quantity squared, which is 1/4. All right, and then let's write this g of f of -2, that is g of 1/4. Now we may go ahead to the function g of x equals the square root of x plus 2, which is square root of 1/4, because that's the x, plus 2. And simplifying these two numbers, well, let's write this as a 2 over 1, multiplying numerator and denominator by 4. That'll be the square root of 4 times 2, which is 8 plus 1, that's 9/4. And the nice thing about this, both numbers happen to be perfect squares. Remember from day one when we evaluate our radicals, well, take the square root of the numerator, which is root of 9, which is 3. Take the square root of the denominator, which is the square root of 4, which equals to 2. All right, and that's our final answer. Okay, they're asking us to evaluate, to find out, to solve a couple more problems. Well, example number 11. Let g of x equals x squared minus 7. Find, actually in this case, they're only giving us one function, so they want us to compose a function with itself, which is possible. You know, it's possible to compose a function with itself. All we do is substitute the function into itself. So what are we going to do? G, circle G, or G bubble G of x. This is the same as saying G evaluated at G of x, where the inner function, that is, so the function we're talking about in this case, that is quantity squared, and that is g of x minus 7. All right, that is x squared minus 7, quantity squared, minus 7, and let's expand the binomial. Again, be careful. You don't want to do the following. Recall, and we have discussed this many times in class, x squared minus 7 squared is not equal to x squared squared minus 7 squared. No, that's all wrong. What do we have to do in this case? Either use the binomial square formula, or simply or FOIL all this. So that is, so x squared minus 7 quantity squared is the same as saying x squared minus 7 multiplied with itself. All right, and simply FOIL. Don't forget about this -7 at the end. All right, so let's FOIL this guy. That means x squared times x squared, that equals x to the 4th. X squared times -7, that's -7x squared. -7 times x squared, that's -7x squared. -7 times itself, -7, be careful, that's the product between two negatives, which is a positive 49. Don't forget about this -7, because oftentimes it's a very silly mistake to make, because we are so busy into this this foiling process that we forget about other terms or other factors. So just beware of that, about that. All right, so from here, I guess we're ready to combine like terms and call it a day for this example. So, sorry. So x to the 4th. There's no other x to the 4th, so this is just x to the 4th. We have a couple of quadratic terms right here. That's a -14x squared, and 49 minus 7, that equals to 42, positive 42. All right. And that is pretty much our final answer. In this case, they're not asking us to evaluate it at a value. So the purpose of this exercise number 11, is just to illustrate that we can compose a function into itself. And we can do it again and again and again and again. We can do that many times, all right, without any bound. All right. So let's move on to a couple more examples on the next page. So suppose h of x equals 5x minus 8 to the fourth power. Find two functions f and g such that f bubble g or f composite g of x equals this big H function. So what are we doing here? Well, this is basically the backwards type of problem that we have been doing. So what did we do in the previous few problems? So we were given two functions, compose them in different orders. We got different results. But this time we're given a function already composed for us. They want us to break it apart into two functions, and that is how we're going to get. Actually, know that when we are doing this process backwards, there is not a unique way to show these parts that comprise the composition. There's pretty much infinitely many ways to get these functions. Again, keep in mind that f is the outer function and g of x equals the inner function. Outer function, inner function. All right, well, so let's see. Let's explore a few options to do all this. So option one. Well, actually, our outer function looks like something to the fourth power, and our inner function looks like this binomial 5x equals to, 5x minus 8. So this means we can call this f of x equals to x to the fourth power and g of x, the inner function, 5x minus 8. Now try this composition. F evaluated at g of x, that equals the outermost, which is something to the fourth power, and the inner, which is 5x minus 8. And see how this result matches our original problem? It's better. All right. There's another option here, option number 2. Okay, can you think of this power 4 as because 4 equals the same as 2 times 2? And well, so how about call f of x equals to x squared? How about g of x equals to 5x minus 8 all squared, which means, and if we compose this, what are we going to get? If we do f and g, f composed with g equals, well, we're going to have something squared. That'll be 5x minus 8 quantity squared. Well, what do we do here? Power of another power, multiply the powers. What is that going to give us? 2 times 2, power negative 8. That means negative 4. All right. Does that look like the original function? Of course, it looks like the original function. All right. Is there another one? Well, of course, option number 3. Option number 3. So for option number 3, we can think of, well, instead as how about f of x? Okay, f of x equals to x minus 8. Okay, let me erase all this. Okay, f of x minus 8 squared, and g of x equal to simply 5x. All right, all I'm doing is replacing this 5x in the original function with simply an x, and later by composition replacing it with what's it called, with a 5x. All right, so this could give us, okay, if we do the composition, f evaluated at g of x that equals um, quantity to the, well, actually it shouldn't be to the second, should be to the fourth power, this one. All right, to the fourth power, and that'll be quantity x, which is in this case 5x minus 8, and then we'll just go, let's just get rid of the parentheses. 5x minus 8 to the fourth power. Is there another way we could do this? Well, yes, of course we can do it. So check this out. Option number 4. So option number 4. How about, okay, um, you can play with the different operations, the different grouping symbols, the different etc. I don't know. Let's say, for instance, f of x. So in this case, f of x, let me leave some room over here. How about what I was thinking of? How about x to the 8th power? Check this out. X to the 8th power and g of x equals square root of 5x minus 8. How would that work in this case? Well, if we do f of g of x equals to quantity to the 8th power, so quantity to the 8th power, that is the square root of 5x minus 8. Well, how about simplify this radical with this 8, because this is an invisible 2, so 8 divided by 2, that's the same, that reduces to the original function we were looking at, 5x minus 8 over 4. So, and we can keep exploring even more ways to come up with a composition. Can we think of more? Well, I can actually think of another one. How about option 5, just to finish up this exercise? I could think of f of x as the square root of x, close the radical, and then subtract 8, and then raise this to the 4th power. How about g of x? G of x being 25 x squared. Well, this one should work, by the way. This one should work because if you substitute 25x squared into this radical, you're going to take the square root of 25 to be this 5 right here, and then you're going to take the square root of x squared, which will be simply x. All right. So that's another way to compose a function and giving us the same composition, or rather to decompose a function to give so that it gets the actual composition we're looking for. But again, these are not unique. There's not a unique way to get these compositions. All right. So of course, if you believe there's other compositions, can you think of other compositions? Well, of course, think about them and they make sure they get you to the actual original function. All right, well, so let's wrap up this notes with one more example. So the area are in square meters of a circular algae colony with radius r meters in meters is given by a of r equals pi r squared. That's just the regular formula to find the area of a circle. However, this radius, it's a function of time, because this time, think of monitoring how fast a colony of algae here is growing or maybe getting smaller as time moves on. And well, looks like time moves in as a linear function, as a linear relation. So they're asking us to write instead of doing calculations into one formula for time and then substitute it into the area formula, we can combine these two functions by finding its composition and simply substitute into one single formula. Well, so well, in this case, they're not, so they're asking us to write a formula for A of t in square meters. So, all right, so let's see, A of t, so A of t will be formed by, number one, A evaluated at R of t, all right? So the same function A evaluated at t. So number one, this is the function, the area function, that's pi r squared, pi times something squared. What is that something here? Well, let's highlight the r of t. All right, let's the r of t. Well, number one, let's write it in terms of r of t. All right, and highlight it in accordance with that same color. Well, that equals pi times our function in terms of t, which is 10 thirds t squared, and in this case, well, that is pi times 10 squared, which is 100 t over 9. And just cleaning this up, how about we write the squared for the t? How about 100 pi times t squared all over 9? And that'll be our final answer. This equation, or rather this function, would be helpful to obtain area starting with time, rather than calculating different radii for time and then substituting those radii into the function a. And this is how we finish this section. Actually, I believe this finishes the chapter. The next on the notes is just chapter 2. All right, let's call it a day here.